Hey guys, today we are looking at 7.3, which is all about special products of polynomials. So today's section is going to be a little bit different, a little bit weird. We're looking at multiplying polynomials together. We're looking at a couple of special patterns. So this will be some shortcuts for us that if these make sense to you, awesome, utilize them for sure. But again, like I said, these are just shortcuts. So they're going to be optional for us. You don't necessarily have to use them right now. Once we get into the second half of this chapter, they're going to be very useful to know when we start working backwards with something that's called factoring. But for right now, if you realize these and recognize them, you can utilize them for sure. They are shortcuts. They will go quicker if you recognize them and have them available to you. But take it with a grain of salt. If they're super confusing to you and they just don't make any sense, that's okay for right now. You can still multiply the old school way. So we're going to look at a couple of just explorations first, just playing around with some different things to see what happens, to see if we can recognize some patterns. So if we're going through and trying to multiply this together, we've got a plus b squared, which we should know from our exponent stuff. If we're trying to square something, something squared is the same thing as multiplying by itself. So a plus b squared is the same thing as a plus b times a plus b. So if we were going to go ahead and multiply that using our box multiplication like I have set up here, we would have a plus b times a plus b. And as we go through and multiply, a times a is a squared, a times b is ab, a times b is ab, and then b times b is b squared. So if we collected up my like terms, we see here ab and ab have the same variable with the same exponent on each of them. So I can collect those together, and we should end up with a squared plus 2 ab's plus b squared. Okay. Flipping around on this other one here, if we have a plus b times a minus b. So if we're going to go ahead and multiply that out, a plus b times a minus b, which would be a negative b. When we multiply these together, a times a, still a squared, a times b, still ab. A times negative b is now a negative ab, and then negative b times b is a negative b squared. So when we look at our like terms, they're actually going to cancel each other out in this case because we have a positive ab and a negative ab. So I end up with no ab's. So I just have a squared minus b squared. So those two things, these kind of what I call shortcuts, they're patterns that we will use to kind of go back and forth between. If we look at what we started with, what was printed there, a plus b parentheses squared, going to a squared plus 2ab plus b squared, that's one of our two shortcuts. And then a minus b times a plus b, or vice versa, being a squared minus b squared after we utilize it, is our other shortcut. So looking at this, we have a special name for this one, that second one that we just finished up, which is, to be honest, this is the one that I utilize more than the other. I don't really utilize that first one that we looked at. This one we use a ton of because it really is shortcut. It's much shorter to go through this process and look at just those first two terms and be able to evaluate. So what our sum and difference pattern is, if we have two parentheses that are being multiplied together, that the first and second terms, the actual numbers or the variables, whatever, are the same, but one of my parentheses has addition in between, one of them has subtraction in between, it always ends up that my answer, my product, is just that first thing squared minus that second thing squared. So if we take a look at what this looks like with some numbers, if we had something like e plus 2 times e minus 2. You can see my first term is e, those are both the same. My second term are both 2, but one's plus, one's minus. So if I wanted to simplify that without having to go through the whole foiling process or the box multiplication process, this, because it follows that sum and difference pattern, is just my first thing squared minus my second thing squared. So e squared minus 2 squared, which we know 2 squared is 4, so e squared minus 4 is what I would get if I foiled it out all the way. So we can just do a couple of extra practices there. X plus 3 times x minus 3. Well, that's just the same thing as x squared minus 3 squared, since that followed my sum and difference pattern. So x squared minus 9, without having to do FOIL. Which, foiling on that, not too bad, but as soon as you hit something ugly like number 2 here, where we've got x squared minus 4 and x squared plus 4, if we were going to go through and FOIL that, some of us would struggle quite a bit. So if we had, like here, we have to square our first thing, so we're going to take x squared, and we have to square that, and then minus our second term squared. So when we square x squared, we have to follow our power rule here. Exponent being raised with our exponent power gets raised to the 4th power now, and then 4 squared is 16. Something that I want to add in an extra little example here. I want to add in a number 3. If we had something like 2x plus 4 times 2x minus 4, this still follows that same pattern. I still have the same first 2 terms, same second 2 terms, 1 plus, 1 minus. What I have to do here, 2x squared, so my first term squared, minus my second thing squared. But when I square 2x, remember our power rule here means that I have to square my 2 and my x on the inside. So what I'd end up with is 4x squared, because 2 squared is 4, and then 4 squared is 16. I would end up with this, 4x squared minus 16. So that's what that looks like. That's our sum and difference pattern. We'll eventually, later in this chapter, change the name of this to the difference of 2 squares, because my answer is literally the difference of 2 squared things. So that's why we call it the difference of 2 squares. That is, I would say, if you're going to take one thing away from this section, it would be that pattern right there. The backside is a little bit different. The backside, it starts off really simple and it gets a little bit messier as we move to the actual expansion of this. This is, we call the square of a binomial. So it's literally just taking some binomial and squaring it, so multiplying it by itself. And we have 2 different versions of this. If you are taking the square of a sum, so a plus b squared, you end up with a squared plus 2ab plus b squared. That's just like we saw on that front page. If it's a subtraction in between instead of an addition, the only thing that flips is this middle term just becomes a negative 2ab. So if we wanted to write out some examples of what this might look like, let's just start with this one. So if we had, I don't know, r minus 9 squared, the way I would do this, so a squared means my first term squared, so r squared, minus 2 times, I'm going to get rid of these parentheses here, r. 2 times a is my first term, is r. b is my second thing, 9, plus 9 squared. So I'm just replacing all of my a's with my first term, all of my b's with my second term. And now I just simplify. So r squared stays as r squared. Negative 2 times 9 is a negative 18r. And then 9 squared is 81. So that would be r minus 9 squared. If we flip over and do an addition one, where we have an example, let's do, I like to change up the variables, j plus 7 squared. If we were to do that, now my a, if you need to write this down, people can. Some people prefer that. My a value is the same thing as j, and my b would be 7 in this case. So in this right side of my equation, I'm going to replace all of my a's with j's, and all of my b's with 7s. That's what I'm doing. That's the process that I'm doing to evaluate here. So if I did that, I'd end up with j squared plus 2 times j times 7 plus 7 squared. So as I go through and simplify, j squared plus 14j plus 49. And that would be my final simplification for that one. All right, so let's go ahead and just try a couple, get some extra practice in here. So we've got a plus 4 times a plus 4. That is the same thing as a plus 4 squared. So here my a is a, my b is 4. So in that sum, the pattern here, we had a squared plus 2 times a times b, which is 4, plus b squared. So we ended up with a squared plus 8a plus 16. And that's my final simplification for that one. And my last one here in these examples, y minus 1. So here my a is y, my b is 1. And since it's subtraction, I'm going to be minusing 2ab, subtracting 2ab. So a squared, which is y squared, minus 2 times my a value of y times my b value of 1 plus 1 squared. So now all we have to do is collect up our like term, sorry, not collect our like term, but simplify this middle term. So y squared minus 2 times 1 is still 2, y plus my 1 squared is 1. Whoops, a little undersold the rectangle there. There we go. So like I said, I'm not a huge fan of that pattern because that right there seems like way more work than just foiling those. So it's not something I usually use for something simple like this. When it's messier things, yes, I do. But for the most part, it's that front side that I really utilize. All right, so some other tricks, some things that we can utilize these patterns for. So for number 5, we're looking at trying to use one of those two special products to be able to find the product, so multiplying 26 times 34 without having to use a calculator. So it's a little bit tricky because it's not obvious to us on how this would apply, but things that I notice here, and again, I'm wired differently. I've got a math brain. Not everyone has a math brain, or at least wired specifically for math. But when I look at 26 and 34, I recognize there that those are close to the same number, right? 30 is close to 26 and to 34. And in this case, actually, 26 is 4 smaller than 30, and 34 is 4 bigger than 30. So what you can do here to utilize that special product rule, if we said that 26 is 30 minus 4, and that 34 is 30 plus 4, that's actually our sum and difference formula, right? That's the difference of two squares. We've got our first things are the same, our second things are the same, one's plus, one's minus. So this is the same thing as saying I could do this as 30 squared minus 4 squared, which becomes a whole lot easier. Most of us could do 30 squared in our head and say that that's 900 because 3 times 3 is 9, and then we need 2 more zeros. 4 squared is 16, so 900 minus 16 is 884. And that's what 26 times 34 is, without having to use a calculator. All right, last thing here, last little special thing. We're asked to write the polynomial that represents the area of the square. Sometimes your book will throw these at you. Here, this is the same thing as box multiplication, which is the nice thing that we've already established that. When we go through and do our box multiplication here, I'm just going to do each individual piece. So we've got x squared times, so 3x, x times 3, x times x again is x squared. 3 times x, 3x. 3 times 3 is 9. 3 times x is 3x. X times x, x squared. Oops. X times 3, 3x. X times x, x squared. And then just collect up our like terms. We've got x squareds in all 4 corners. We've got x's on kind of the side pieces. And then my 9 is just all by itself. So if we find our final representation of the area, we should end up with 4 x squareds. We've got 1, 2, 3, 4, 3 x's, so that's a total of 12 x plus 9. There's the area of that square. That's all I got for you guys for today. So your homework is up there on the screen, page 375, 4 through 30, just the evens. As always, if you guys have any questions, concerns, thoughts, ideas, hopes, or dreams, make sure you guys are reaching out and letting me know. Otherwise, have a fantastic day. We'll see you soon.